My background, I've been doing machine learning, deep learning for about 5.5 years. I started with piano, and I've spent some time at Columbia University working in NLP, at Google doing deep learning for hate speech detection, and in my previous company we built a chat analytics app, so we get to deploy about 50 NLP models to productions in about 15 different languages, and kind of working in those teams we realized there's a lot of problems that needs to be solved, except of course the research and the algorithm side. So I'm just gonna walk through like a really quick demo, and if anyone has questions, like Cece said, we'll be around, so feel free to stop by and ask anything. So I'm already logged in, so this is what it looks once you sign up for the first time. It's Comet.ml. It's completely free to sign up, and as you can see, we kind of support all the popular deep learning and machine learning libraries, but if you're using something that's not listed, there's also a custom API. For this demo, I'm gonna pick Keras. I'm just kidding. We'll go with PyTorch. Once you pick your machine learning library, the only thing you need to do is kind of pip install Comet.ml. And then depending on kind of like the use cases, in most cases, the only thing you need to copy paste is just like this two-liner that creates an experiment object. This has a few other examples. To avoid kind of the Vim versus Emacs discussion, I'm going to go with PyCharm. I hope that's okay with everyone. So I have some example code here on the MNIST dataset. It's really straightforward. I think it's from the PyTorch tutorial. It's actually training an RNN on the MNIST dataset, which is interesting. But there's nothing special here or no Comet code. It's really just simple model. And we threw here this experiment object that we created. So an API key is my personal API key. Project name is usually a business task or a specific model that you're working on. And workspace is if you have multiple teams. And essentially here we're also logging our hyperparameters. So I'm going to train this model. I'm going to train it on my laptop. What's really cool is it doesn't matter where you're trying to model. So you can train it on your laptop, on your private cluster, AWS, GCP, as long as it has an internet connection, it will work. And as soon as it starts training, it should give me a URL to the model. So give it a second. I'm also running dev environment, but this says experiment is now live on Comet, and I can click this thing. Sweet. So the first thing I kind of see are my metrics. So here we have loss and training accuracy. We actually extract loss automatically because we can use it. We're using AutoGrad on PyTorch, but we reported accuracy as well. And if you want to look at something like loss versus train accuracy or anything like that, you can of course create your own charts and see that as well. We also track all your code, so it's fully reproducible. You always know what code generated what model, what result. All your hyperparameters, metrics, this is more information about the graph definition, standard output, so if you're training 20 models, one of them throws an exception, you don't have to SSH into containers. System metrics usually would show GPU utilization, but this is a MacBook. All your dependencies, you know exactly what version of PyTorch you use to train this model. And you can take notes, and I'll show you a little bit more after that. But I want to go click this link here that says Meetup, which is our project name. So here we actually see we have 3 models, 2 of them that I trained a little bit earlier today. And we can actually see kind of like all of our models over time. But I think one thing that's really cool is we can see that we have 2 models here, and there's like a 4% absolute difference in accuracy. So what I can do actually is select them and hit diff. And then I can kind of see how they converge differently. But if there's changes, I can actually see what changed in the code. So as you can see here, we reduced the hidden size of one of the layers and removed actually one of the layers. And we should see the same thing here also on the hyperparameter side. So we kind of allow you to compare every piece of it. One other thing I want to show you is like sometimes if you've probably been training models, you have more than just 3 experiments. So I'm going to switch to a project that has a few more of this. So this is actually a project with, let's see, like 23 experiments, right? And I just want to show you one thing. I'm going to switch this to the wide. So one of the things we allow you to do is kind of analyze the hyperparameter space. So I don't know if anyone's seen this type of chart before, but every axis here is a different hyperparameter. Every line is a model or an experiment. And the more orange the line is, the higher the validation accuracy in this case. So if you look at this kernel size column here, just by eyeballing this, you can tell that if I set my kernel size to 5, I actually tend to outperform all my other models. So I can actually select this, and then the rest of the charts update as well, so I can look at accuracy and loss over time. But more specifically, I can see in the table these are the visible experiments and select one of them and kind of dive deeper into the code. One other cool features I want to show you that for those of you who are working on vision, so this is actually a project, public project, so everyone can visit this. And this is a user that's working with satellite images to detect forests or trees. So we've already seen this view, but I'm going to switch to this graphics tab. And you can see he's reporting data from his test set during training. So 064 here is just one instance, so it's repeating the same instance. So let's actually take 063. And you can see that the step changes. So we're looking at the same image being predicted or classified by the model over time during training. So for example, let me see an example here. So one of the things you can see here, so there's a tree here at the bottom. I think at some point it finds a few more. And you can actually also make like an animation. So you can kind of see how the model predictions change over time during training, which is really useful for debugging and so on. Yeah, so I don't want to take, again, too much of your time. I want to thank you again, everyone, for coming here today. I'm really looking forward to hear the talk. If you work in a machine learning team, run a machine learning team, and want to discuss more about visibility, reproducibility, and how to make those teams and processes more effective, I'd be happy to have a conversation. I'll be around here.
So, at the very core, a training loop is just an iteration of all those post input steps. You have training data that's labeled. You feed it through a model. You compare your output of the model with targets, and you compute a loss. Then you use this loss to compute gradients, which you will then use to do a step of your model. So that hopefully at the next iteration, it's going to be a little bit better. And you do this repeatedly until you're satisfied with the final loss or accuracy you're getting. And in PyTorch, that's very simple to write. It's basically the 4 instructions plus a little bit. So you have to remember to set your model in training so that drop-offs or batch norms behave properly. And then this is the iteration of the training data. Using PyTorch data loaders, you compute an output from your model, then a loss that backward computes your gradients, and then the PyTorch optimizer does a step for you. You just have to add this little line to remember to zero all the gradients of your model. So that's pretty simple. The problem is that there are multiple tricks that you can and that you will have to add to your training loop, and those 5 lines of code from before are going to soon become pretty messy. So what kind of tricks are we talking about? The first thing is that you will want to keep track of your losses and metrics, so maybe using Comet maybe just recording your losses and accuracy, maybe using TensorBoard, and all of that is going to require additional instructions inside the training loop. Then you'll most probably want to do some kind of hyperparameter schedule, whether you drop your learning rate every n epochs or whenever the validation lot doesn't improve, whether you're using stochastic gradient descent with 3 stars at the top, or the one-cycle policy at the bottom. And then every paper comes with new regularization techniques that you will probably want to try. So there are a lot of them, I just listed 4 that I like. For instance, stochastic weight averaging. If you're using the gradient descent restart that we just saw, this consists in averaging the weights at each bottom, so that at the end your model is kind of an ensemble. The weight decay, and more generally, there are several ways you can do your weight decay. So this is the Adam W. paper that suggests to do it outside of the PyTorch optimizer or the TensorFlow optimizer. So that, because otherwise it's not exactly weight decay, but auto-regularization. Mix-up, which is one of my favorite data augmentation techniques, where if you're in image recognition, you feed to your model, let's say, 0.3 multiplied by your image of a cat plus 0.7 multiplied by your image of a dog, and you ask it to predict 30% cat, 70% dog. And surprisingly, it works super well to get a better accuracy. And all the various techniques to get all the various penalties that you add to your loss so that your model generalizes better. So this is in RNNs. Often you want to not only use auto-regularization, but add a loss penalty that comes from the hidden states of your RNNs. Or the second equation is when you want to use temporal regularization, you use a penalty to make the difference between two consecutive hidden steps as little as possible. And I'm not even talking about the very big stuff that requires a lot of changes for a training loop. So one example is mixed precision training. So if you've never heard of it before, it's when you want to use half precision flows. So usual flows that we use all the time take 32 bits in memory. And there is another type that's called half precision that use half of that, which is very good because it's going to take less memory on your GPU and also on the very modern the GPUs from NVIDIA, you can have a split factor up to 4 items faster because they optimized for it. The problem is that you can't train all your model in half precision, otherwise your training won't converge. So you have to do this thing called mixed precision, where you do half of your training in full precision and the other half in half precision. So I'll come back to it later, but basically you have to do a lot of tweaks to your training loop that are represented by this diagram. And then there are GANs, for instance, where you are training one model against the other. So this is also going to take your training loop and multiply the number of instructions by 2 roughly. So how do you keep with everything without becoming too messy? So the regular approach that you see all the time is that you write a new training loop each time you have a new project. Basically, in each repo. On GitHub, you often see that there is no for each trick of the hyperparameter, you have a new training loop that's appearing. The other technique is to try to write everything in the same place, but it becomes super messy. So it's super hard to debug, and if you want contributors to add a tweak or to use your training loop, they're not going to be able to understand it. So if you can't change the 5 instructions that are the core of the training loop because you don't want it to become too messy, you have to write it outside of it. That's when callbacks come into the game. So if you go back to our training loop, the basic one with its 5 instructions, we change it by just adding callbacks between every step. So we can still see the 5 original steps here in red, and then basically between each instructions, I added calls to some callbacks. This is a good start because we are going to be able to run additional code between every line of the training loop, so theoretically we can write anything we want, but it's not going to work for the simple reason that those callbacks don't know what's happening inside that training loop. So if we want to be able to tweak everything, we need to be able to see everything, and we also need to be able to change everything inside those callbacks. So that's where we designed something called a system with a callback handler that is responsible for taking all the states of the training loop and feeding it to each one of the callbacks you want to use. So you may have one callback that will be responsible, for instance, for your hyperparameter schedule. There's another one that can record your metrics, another one that's going to do your mixed precision, etc., etc. At the center, you have the handler that's going to collect every information from the training loop. What is your model? What are your inputs? What are your targets? What is your loss? And then each callback can analyze that state and then modify it. For instance, if you're adding something to the loss, you need to be able to tell the training loop the loss has changed. I've added that little bit to it to do some regularization. If you change some learning rate, for instance, again, the training loop must be able to know it, otherwise it's not going to work. So if we go back to the code, we did that with 2 things in Fast.ai. The first thing is that we've gathered all the general context. That's the thing that don't change during the training loop: your model, your loss function, the optimizer, and your data. which we gather in an object called data bunch that contains a training data loader and a validation data loader, both being regular PyTorch data loaders. And I'm insisting a bit over it because if you're not using Fast.ai but are using PyTorch, as long as you have those things, you can use your training loop or callback system without any kind of problems. So that's a little bit of shameless advertisement here. And so that general context is gathered inside one object called the learner, because in PyTorch objects are mutables. So if we pass that learner to all the callbacks, they can change any of those attributes, and it's going to be reflected everywhere. So if we go back to the training loop, it's become a little bit more messy, but it still fits in one spin of code. The 5 instructions we saw as in the beginning are here. And I just added one more instruction of code which concerns validations and metrics. All the rest is just callbacks. It's become a tiny bit more complex because we need to tell those callbacks everything that's going on. And then they also need to be able to change things and maybe take decisions. So for instance, at the very beginning, we initiate our callback handler I was talking about previously. Then the event onTrain begin. We pass all the context. So that's hidden inside that learner, the metrics, and the number of epochs in our training loop. And during that callback, during that event, every one of our callback is going to be able to initialize its states properly. Then we don't forget to put our model in training, and just after that, at the beginning of each epoch, we have the event onEpochBegin, again for initialization, onBatchBegin. But as you can see, it's a little bit different than the 2 previous events to callbacks in the sense that it returns something. It returns a potentially modified input and a potentially modified target. For instance, if we were playing mix-up, there is inside that call on batch-begin one callback responsible for mix-up that's going to take 70% dung and 30% cat and modify the input in consequence, and also the target, telling the model it needs to predict 70% dung and 30% cat. Same thing for the event onLossBegin. It returns the potentially modified output of your model if you had some post-processing to do. Then the next event takes the loss and returns a potentially modified loss if you wanted to add some penalties, and also a flag that's going to tell the training loop to skip the backward pass if for some reasons you don't want to do the backward pass during that iteration. And same thing. All of the next callback events return a boolean that tells the training loop if it should, for instance, not do the optimizer step. That's very useful if you want to accumulate gradients for a few batches before doing the backward pass. The step of the optimizer. Same thing for the ring the grad. At the onBatch end event, you can tell the training loop to just stop. For instance, if your loss became in N, you don't want to continue your training. And it's the same for the event on epoch end. If you are using an early stopping strategy and your validation loss hasn't improved, for instance, you might tell the training loop to just stop training altogether. And then the final call is just there to do some potential cleanup after everything that happened. So let's look at some examples of what those callbacks can look like. The first one is very basic. We want to schedule some hyperparameters. So each callback receives, we've used a dictionary to contain our state, so it's very easy to then pull the information you want from it because we just pass it up to quarks. So for instance, there is an iteration key in that dictionary, and by saying iteration quarks, we've just pulled that value. And then we use whatever function we want from that iteration to change. So if you remember previously, there was a learner object that had an attribute for the optimizer, and we changed the learning rate. Same for early stopping, it just takes one line at the event onEpochEnd. We check the last metrics, and with some function of those last metrics that's going to tell us when to stop, we return a flag to tell the training to stop. The parallel trainer is very useful because if you use PyTorch to do training on multiple GPUs, very often you can have some problems when the training has ended because your model is across several GPUs, so the callback does the data parallel wrapping and then the wrapping at the end of the training for you. Gradient clipping is another simple example. where we just clip all our gradients. So on backward n is the event that's called after the backward pass has been done, but just before the step of the optimizer. Then if we can look at an example that's a little bit more complex. So this is the callback in Fast.ai that does accumulate gradient. When you have a batch size of 2, for instance, because your model is huge and nothing else fits in your memory, you need to do a few iterations before actually doing the step of the optimizer. So again, super easy to do. At on epoch begin, we just initiate our contours. We increment that at each on-batch begin event, and then during the on-backward end event, which is again after the backward call and before the optimizer step, if it's time, we're going to do an update. Just before we do the update, there is a tiny tweak to do is that all the gradients need to be divided by the number of samples you've seen, otherwise it's not going to be the regular mean over the batch. And you return, if it's not time to do an update, you just return the 2 flags that are going to tell the training loop to skip the optimizer step. And lastly, on epoch is just there to even potentially do an update or not, depending on the value of the flag, and always zeroing the gradients because we need them properly cleaned for the next event. So with that system, it's really easy to mix and match the blocks you want to add to your training loop or not. So this is going to be very useful if you want to do ablation studies, for instance, so to be able to completely get why your model is training so well, and without having to rewrite each time you're training loop. It's also very easy to add a new little bit. You just have to write a callback like we just saw. So this offers total flexibility. And with the last 2 examples, I've taken the two things I talked about that are very, that modify the training loop a lot to just show you and try to convince you that it's really letting you do anything you want from the training loop. And then, so in Fast.ai, to call those block callbacks, it's just that simple instruction that tells the learner to be fit for a certain number of epochs, learning rate, rate decay, and then all the blocks you've selected as callbacks. So, one example that's a bit tough, that was a bit tough because now there is a library for NVIDIA that does it automatically for you, but that used to be very tough to do in a training loop. So, mixed precision training. So as I said before, mixed precision is when you use float 16 instead of regular floats, which they take less space in memory, but they come with a disadvantage that they don't have the same range. You can see at the very bottom. So they're going to become 0 more quickly, like at 10 minus 10 in 5, and they're also going to become in the end on the other direction very quickly. So when you're training, you apply your model to your input to compute the outputs in half precision. And then the first thing is that you have to compute the loss in full precision. Why is that? It's because otherwise your loss will have a tendency to overflow. So if you don't compute it in full precision, you're going to be sometimes above that range, the maximum range of the FP16s, and have a training that goes completely wrong. Once you have computed your loss, you scale it, which seems weird, but that's to take care of the other problem. The other problem is that gradients are very low numbers. So if you compute your gradients in half precision, which is what we're going to do, you have a very good chance that a lot of your gradients are going to become 0 just because they fall under the lower range of the range of FP16s. So to avoid that, you multiply your loss by a big number to make all the gradients be a little bit bigger and take all the space they can in that normal range. Once you've scaled your loss, you do the backward pass, and you have your scaled gradients. You copy them because one thing that absolutely needs to be done in full precision is the model update. So since you're doing the model update in full precision, you copy your gradients from FP16 back to FP32, and then it's safe to unscale them because you have the normal range of floats, so there is less chance that they're going to become zeros. You have a copy of your model weights that are in full float precision to do that update. So you do that update in full precisions, and then you copy those master weights that are in full precision to the weights of your model during the final step to be able to do the next iteration in half precision. So, like I said, you need to have the model for evaluation and backpropagation that's going to be in half precision, and your optimizer needs to be in full precision, otherwise your update is not going to be precise enough and your training isn't going to converge. So to do this, in our mixed precision callback, the first thing is to create, but at the bottom, the first thing we do is we create two copies of the model. The first one in half precision for computing outputs and doing the updates, computing the outputs and the gradients, and the second one for the update in full precision. And the last line is to change the optimizer that's used during the training loop to use the optimizer that's going to use the model parameters in full precision. Then it's super easy with the callback system to match that diagram and do in each green arrow what we need to do. So computing the output of the model in half precision, that's going to be automatically done by the training loop. Then to be sure that the loss is computed in full precision, we take the last output and we return it modified just by putting it back to float. The scaling is done during the on-backward begin event. We multiply the loss by a loss scale, so by default something like 512, and now in the second version of their mixed precision training algorithm, NVIDIA suggests to use a dynamic loss scaling that begins very high until the gradients stop overflowing to be able to use the full range that you can, the biggest range that you can. Then once the back propagation is done, you copy, that's the first line, you copy the gradients to the master model, and then it's safe to unscale them and clip them if you wanted to have some clipping. Then once your step is done, you have to remember to zero the gradients of the model. Why is that? Because the regular model has been disconnected from the optimizer that's used inside the training loop. This optimizer is using the master model. And then once the update is done, you copy the weights from your master model to the model in half precision for the next step. So that thing that looked like a lot of work and that would have changed your training loop a lot is fairly easy to do in a callback. And the good thing is also that once you've done that callback and you've debugged it, you don't need to think twice about half precision again. And the next time you're writing a new training loop that is going to use that, you can just call that block, and it's not going to be a new pain to debug. Another thing that you can do with that callback system without changing a single line in the training loop I showed you is GAN trainings. So in GAN trainings, you're training two models, one against the other. A generator is going to try to generate images from random noise, and the discriminator, or the critic, is going to classify the images, the fake images from the generator from real images in your dataset. So to do this with our training loop, we just had to add a few tweaks. The first tweak is that we need to define a kind of super model that's going to contain the two models, the generator and the critic. And during the forward pass, it just, depending on an inner variable that tells it if it's in generation mode or not, it's going to switch the arguments to the generator or the critics and dispatch properly. And then it has a switch function that tells it to change its state from generator to critic or critic to generator. We do kind of the same thing for the loss, which needs to be able to do either generator or critic. When the loss is there to evaluate the generator, the output of our model is a bunch of fake images. So we use the critic to determine what are the probabilities according to the critic that those images are fake, and that's used to compute the loss. We also add the initial targets, that's a bunch of real images, and the output is a bunch of fake images, because sometimes in GAN trainings, people want to mix the critic and then some pixel loss or some content loss or some style loss, depending on the problem you're tackling. The loss for the critic, so once the critic has evaluated an input, it gives what it thinks is the real predictions, and then we need to take a batch of from that randomness, we need to generate a batch of fake images, and then the fake predictions that goes with them that are going to help us compute the loss function. So for instance, if it's a Wasserstein-GAN, it's just the difference between real and fake predictions. And then our GAN trainer is a callback that is responsible for switching in and out and making sure that the right inputs and targets are given to the model. So the switch is just telling it, so there is again a flag, changing the optimizer, because depending if we're training the generator or the critic, we need to update the parameters of the generator or the critic. It's responsible to tell the loss function of the model, which generative mode to use. And then it's also responsible to put all the parameters in either requires WAD or not requires WAD, but just to make sure that we don't use too much memory. So for instance, when we're training the generator, or what's called train model is a generator, loss model is a critic because it's only used for the loss, and we don't want to compute the gradients for all the parameters of the critic because that's not useful, and it's going to take too much memory. Then the callback itself, at the very beginning, there is a lot of stuff to do because we have to instantiate the two new optimizers that are going to take care of the steps for either the critic or the generator. Then the untrained event is just switching, making sure everything is switched to generation mode, because usually when training is done, you want to see results, and results are generating fake images. The unbatch begin event is responsible to give in the right orders inputs and targets. So inputs are random noise, target are the real images. So when we are in generation mode, we take the random noise to generate fake images. So our input is that random noise, and then the target is the bunch of real images. But it's the opposite when we are the critic, because the critic is evaluating the real images and using the random noise to ask the generator to generate a bunch of fake images. On backward begin is just some recording of losses, and on epoch begin is just making a fake switch because at the end of an epoch, since at the end of an epoch, sometimes we put the model in evaluation mode, we need to make sure that everything is back to train or evolve, depending on if they are the critic or the generator. And on epoch, I'm recording some metrics again. So there is nothing to switch in that previous callback because that's done in another callback, which gives you the flexibility to use something that's going to switch either every n iterations, or when the loss of the critic, for instance, is too low, we switch to the generator, and when the loss of the generator is too low, we switch back to the critic, or a mix of both those things. So I just showed the basic fixed switcher. So let's say that we do, for instance, 5 iterations of the critic and 1 iteration of the generator. At the beginning of training, we initiate counters to 0, and then at unbatch end, we increment them. And then depending on whether we've done enough step or not, it's just a tiny bit complicated because the target can be either a constant int or a function, if you want to do something a little more funky. And if it's time to switch, you switch and you set back the counters to 0. So that's all for training GAD. And so what I hoped I showed you is that the callback system that we developed helps keep the training loop as simple as possible. Have each tweak you want to add to it written independently in its own callback so that it's easy to use or not use, depending on what you want to do. Easily mythical mash. Easily add any new experiment ID. Usually when I try to implement a new paper, it's very often a few lines in a callback. And then if it was using some other IDs, I just have to pull the right callbacks from the library. And it makes super simple for any contributor to add their own ID. And like I said, you can use all of this by installing Fast.ai and putting your data, your model, your optimizer, and your loss function in one of our learn objects. The Fast.ai library is on Conda and Pips, super easy to install. That's pretty much it. Thanks a lot for listening to me and for being here tonight. Any questions?
Hey, thanks. I was wondering if you could talk a little bit about if you're combining or mixing start of like a list in which you do the handle?
Very good question. I don't know if you noticed that I didn't comment on that. It's true. Each fallback has an order attribute so that they are then sorted by order. So for instance, the mixed machine fallback is always running at the end because it needs to be shown as the last activity before doing all the shading as it needs to do. But there is an attribute for that, which makes them go in the order you want.
Any other questions?
Can a callback have a callback in it?
In a way, because it has a learner object, and then the learner object has attributes all the callbacks that you define. So again, I didn't comment on it because I didn't dig completely into the code, but for instance, when we were training GANs, the GAN switcher was recovering the GAN trainer callback to know if it was generation mode or not in generation mode.
So there was something called TorchNet that was released about a few years ago. That was released for the Torch framework, and then there was a code. It was very similar. It had something called the TorchNet engine. It was a framework in it was an ugly framework at the British SCA, and then the training group itself was part of something called the engine. I was wondering if you looked into it, if you evaluate that. It's very similar to this. I guess your framework was a little further than what it does. It's far more simple than what it does. And if you look into it and what some of the drawbacks and why you decided to this framework, why not?
No, we haven't looked into that. I didn't know it existed. The initial inspiration was a fallback system in Keras, and then we just made it more complex and more flexible. Sorry.
Okay. So, I know you said it's infinitely customizable, but as you're working on it, is there a use case that you found certain limitations?
We've tried to address them. So, for instance, the flags that was in the training group that to the economical state or something like that, but those were pretty recent because someone wanted to do ingredients. Oh, it's possible. And we found a way to make it possible. So we try to, each time someone comes with a problem that seems impossible to solve, we try to find a way to make it possible and eventually create this solution.
Do you have a standard way to handle checkpointing and then loading the checkpoint continuum from midway through a trainer?
You mean callback for that?
If you have a callback at a state, you have a way to save that state and then load and continue after.
Yeah.
It's a standard method if you're simply yourself.
Yes, so again, I didn't go inside to the full code, but each callback can specify which attributes should be saved or not. By default, it's all of them, but if you have like some maybe attributes you don't want saved, and whenever you save your learn object, it exports the state to the code.
Yeah, thanks for the talk. This might be like a wild idea, but like if you took this like even further, could your training loop ever just be like all callbacks? So you just have like 6 or 7 points at which functions were called, and so even like the basic training loop itself would be like the default callback in that system, and then I don't know if you thought about that or if that would be possible, more convenient.
We've tried to simplify it further. Jeremy is going to show a little bit more work as an export actually, but it's not to the point where it's like just one function and one fallback containing all the others.
Were there any other approaches that you consider to like implement this infinitely customizable loop?
Not so much actually, because like I said, the initial solution came from the fallback system in Keras, and we went like at first along that approach and just made it like a present.
Typically when you write code like this, there's the classic trade-off between what you win in kind of keeping your code dry, and what you lose thereafter is the ability to debug, and also the learning curve that's required to actually kind of get up to the framework. Can you speak to that trade-off a little bit?
So for the end to debug, it's actually the opposite I found, because when you write a new training loop, which is a new part, and you come across the same bugs, and you, I mean, sometimes you remember that, sometimes you don't remember that, and very often you end up doing the same debugging steps that you've done before. So I found it's actually pretty easier to debug this way. As for the learning curve, yeah, you have to learn to use it, but I don't think it's that horrible. At the beginning, you just have to, you have a template that you can copy and paste so that you can see all of the events, and then you just need to remember what are all the variables that you can pull from the state. So there are a bit of names that you need to know. Otherwise, it's not, I don't think it's a value that is rare to master. And we had a few contributors, like quite a few contributors write their own callbacks. So I think they didn't tell us, indicate that they found it very dry and very hard to understand.
How do you document the ordering of your callbacks so that new people, when they write a callback, they don't run over their callback?
Very good question. Actually, we don't. So we are pretty much the only ones that know in which order we're run. But yeah, that's definitely something that's good. I mean, the order is more like there are things that need to be run at the very beginning and things that need to be run at the very end. There's no intricate relationship. It's more like beginning or end. But and we're thinking of trying to build some kind of relation graphs instead of saying in order, saying that that callback is to run after or before that callback. That's the next step we're looking at.
Any other questions? Going once, going twice.
Thank you so much for coming. I had a general question for you as well. If you could speak to the future of this type of development in Fast.ai and what you're working on next in Fast.ai.
So for now, we're mostly working into the course that's running, but the next steps are like I said, making it even more flexible and easy to use. So we've done some steps as well that, but we just talked about the order that's not documented and how we can better it. But yeah, no, so the future is basically the ML is going to be a super object called a runner that's going to contain all that state, and all the callbacks are going to pass that directly. It's going to be a little bit more easy to use. Like the same thing I noted.
All right, we can take one more question after Alex's.
Okay, yeah. So in your slides, you show a lot of snippet codes that look like cells. In your slides, you showed a lot of snippet codes that look like they are cells, they are cells. Do you have some best practices on developing with some group, or what's your thoughts on that?
Sorry, I was half focusing on the nice to.
Oh, sorry. So in your slide, you showed a lot of snippet codes that look like Jupyter Notebook cells. Do you have some best practices with developing Jupyter Notebooks, and what is your thought?
That's a risk of asking if I only use Jupyter Notebooks to code and develop, so that's why we are starting from that. So that's why I debug and implement new things.
All right, I'm talking on the run now. But thanks again, Sylvain, for presenting tonight. Sylvain will be here for a little bit longer if you have questions for him in person. And I also want to thank you again. Just a couple of announcements. One is if you're hiring for a data scientist or machine learning engineer, I actually curate a machine learning jobs newsletter. So if you're interested in that, come talk to me. Gideon's still over here. If you want to talk to me about Comet.ml, if you want to sign up, there's actually a URL right there. It's pretty simple, www.comet.ml. If you'd like to start earlier today in the demo. But thanks everyone for coming. Hope to see you again for the next month's meetup. Sorry, one more last thing. So your ratings are what keep our meetup community alive. If you want to give a 5-star rating, please feel free to do so. If you want to give less than that, just come talk to me directly. We're open to feedback as well.
And one final announcement. So I'm one of the organizers of the PyTorch Meetup. If you're interested in speaking or know someone who would be a good candidate for speaking at the event, please come and reach out to me afterwards. Thank you very much. Have a great evening.